I want to go through one more example of a two-player zero-sum game to show you how to find a Nash equilibrium and the value of such a game. The idea behind this approach is the same as before, but the specific execution is slightly different, so it might be an interesting example. Consider the following game in which player 1 has 2 strategies and player 2 has 3 strategies. What I wrote down here are the payoffs to player 1. The payoff to player 2 can be derived from this because it is a zero-sum game, so the payoff to player 2 is just always minus the payoff to player 1. Because in this game player 1 has only 2 strategies, we can completely specify a mixed strategy for player 1 by stating with what probability the player plays the strategy T. T stands for top here. Say T is played with probability lambda. Then the other strategy, strategy B, which stands for bottom, must be played with the remaining probability. And so the remaining probability is just 1 minus lambda. What is the expected payoff to player 1 if player 2 plays strategy 1? Clearly it is 0.8 times lambda plus 1 times 1 minus lambda. And this is just equal to 1 minus 0.2 times lambda. If player 2 plays strategy M rather than strategy L, by the way, L stands for left and M stands for middle here, the expected payoff is simply 1, no matter what player 1 does. And finally, if player 2 plays strategy R, which stands for right of course, then the expected payoff to player 1 is lambda plus 0.8 times 1 minus lambda. We can plot these 3 functions. The expected payoff if player 2 plays strategy L depends on lambda like this. For strategy M, it is like this. And for strategy R, it is like this. Player 1 wants to maximize her guaranteed expected payoff. For each value of lambda, the expected payoff that player 1 can be guaranteed to get is only the lowest of the 3 functions at that point. This is because we have to assume that the strategy that player 2 picks is the worst one for player 1. So player 2 would always pick the lowest of those 3 functions. So the guaranteed expected payoff to player 1 is the lower envelope of the 3 functions. And it looks like this. Now, player 1 wants to maximize this guaranteed payoff. That means she wants to pick lambda, and therefore a mixed strategy, such that the lower envelope of the 3 function is maximized. Clearly this happens at this point in the middle, where lambda is equal to 1/2. The maximum strategy is 1/2, 1/2. So strategy T is played with probability 1/2 and strategy B is played with probability 1/2 as well. And we can already determine that the value of the game must be 0.9. We can see that playing strategy M is not a good response for player 2 to this, because this would give player 1 a larger expected payoff than either of the 2 other strategies. I mean, in this case, she would get a payoff of 1 rather than a payoff of 0.9. So player 2 would never choose the strategy M here. Player 2 will instead mix between strategy L and strategy R. And it turns out that choosing strategy L and strategy R with probability 1/2 each turns out to be the right approach. And maybe think for yourself of why this is the case, and particularly how you can derive this systematically. Now, if you multiply the payoff matrix with this mixed strategy, which is like 1/2 for left, 0 probability for M, and then 1/2 for the strategy R, we see that in this case, strategy T and strategy B both give an expected payoff of 0.9 to player 1, but not more. So this must be the correct minimax strategy, right? So player 1 can guarantee a payoff of 0.9, and player 2 can guarantee that player 1 doesn't get more than that. If you want to practice this more, you can just write down small payoff matrices with like arbitrary numbers in them, say where both players have either 2 or 3 strategies, and try to find a Nash equilibrium and the value of the game. As we have seen and proven, every two-person zero-sum game must have one of those Nash equilibria. So there always is a solution that you can find.